Hi, in this video we will talk about the Fibonacci sequence. We will talk about the golden ratio, why it is golden and why it is the divine proportion. We will do this by talking about irrational numbers and decimal expansion. The purpose of this video is to show that math is awesome. It is so cool. If by the end of this video you think that math is interesting, then my goal will have been achieved. Which one of these rectangles would you say is the most perfect? Which one pleases you the most? Did you say this one? This rectangle is said to be the most perfectly balanced rectangle of all. What if I was to ask, what about these triangles? Which one do you think is the most perfect? Would you think is this one? Then you'd be again right. Just as the rectangle, this triangle is said to be the most perfectly proportioned triangle. What about these two? Not so much. You! Gross, take them away. These two figures are said to have golden proportions. They are said to be divine. But why? Why are they said to be divine? Where does it come from? Well, to learn where it comes from, we have to go back to the 13th century. In the year 1202, there was this guy called Leonardo of Pisa, now called Leonardo Fibonacci, that imagined an ideal society of rabbits. In this society, why is it so ideal? It's ideal because they reproduce in a perfect manner. To make it simple, the rule is each couple will start reproducing after their first month of life, which means that when a couple is born, he needs 1 month until it is capable of reproducing. From the visual representation of this society's population, we can see that it's simple to know at each month how much rabbits there's going to be. The formula is simple. It's the number of new rabbits plus the number of rabbits that are old. And this is actually pretty simple because the number of old rabbits is the number of rabbits there was the month before. And the number of new rabbit is the number of rabbits there was 2 months before, because the number of rabbits that was there 2 months before, they are all now able to reproduce. So it is this exact number that there will be of new couple. Now that we've established that this civilization is constructed by a sequence that has a logic that says that each new number is the sum of the two previous, let's see what we can do with it. Now that we've gone up to 12 months or 144 couples, let's see what we can do with these numbers. As you can see, if we make them squares, we can display them in this particular manner. Now, from this pattern, you might recognize this curve that is being traced. It's a golden spiral. But why does this golden come from? Why is this pattern golden? Why is it so important? Well, it's because there's a ratio that is very important that this pattern has. Every time we did a new rectangle, it had the same proportion, because this is the basic property of this ratio. Each time you create with this rectangle that has a golden ratio a new rectangle, it has the same ratio. and it goes with this sequence. But why is it important? Well, look, to see how cool it is, we just have to take golden triangles where the ratio between the side length and the base length has the golden ratio. It's a triangle that has angles of 72, 72, and 36. If we take one of these triangles and we put it in a bigger triangle, we create in blue a golden gnomon. And look at what can be done with these forms. That's right, you can make a regular pentagon. Isn't it amazing? Now let's see the next thing. Oh yes, you're starting to see it. You can create a basic pentagram, or more commonly known, a star, from this golden ratio. Isn't it incredible? I think it is. We've established that this golden divine ratio is so incredible, we have to ask ourselves, why is it golden? Why does it have this attribute that's always given to him? First, to explain it, we need to dive inside of the irrational world. An irrational number is a number that cannot be expressed as the ratio of a number which is an integer over another integer. You must know multiple irrational numbers, just as the square root of 2, or the square root of 3, or the square root of 5. You might know the Euler constant, or pi. To understand what an irrational number is, we need to look at its decimal expansion. Let's begin with the decimal expansion of pi. If we chop at the location of the line, the expansion, we can get 3 as an example for the first chopping. For the second one, we chop it at 7. So we have 3 plus 1 over 7, and we ignore the rest. So this is what we're going to do, and we're going to see how good of an approximation we can get. There we can see that if we stop at 292, the approximation is really good. After only 5 steps of the decimal expansion, we can get up to 9 digits of precision. I will compare it with another really well-known irrational number, which is the Euler constant. From the Euler constant and expansion, we can see that after the same number of steps as pi, we get a much less precise approximation of the Euler constant. This is due to the fact that with pi, we at some point, which is at the 5th step, had a really big number, which is 292, which meant that the number before was almost an integer, because the next fraction was so small. This means that this integer over integer is almost as good as the value itself of pi. Here it's very different for the Euler constant, because we have 2, 1, and 1 again. So this shows that it's gonna be really long until we have a big number to approximate the Euler constant. So from this, we can try and figure out what would be the most irrational number there is. Let's, for the moment, call it x. The most irrational number is a continued fraction of 1 plus 1 over 1 plus 1 over 1, and this to infinity. It's actually pretty simple to solve this. We only have to notice that this continued fraction is exactly the same as the part under the first fraction because it's to infinity. This means that we can replace this bottom fraction with x itself. From this point, it's pretty easy. It's a polynomial. We only have to use the quadratic formula and we can solve this and we can get two values for the most irrational number. The symbol of this number is phi. And you can see the decimal approximation that one and the other have the exact same decimal expansion. And it makes sense because we want them to always have the same decimal expansion. So when we do the fractional expansion, it never decreases. It never gets to a bigger number because it's always gonna have the same expansion. Now let's look at this golden number. Let's look at phi and its decimal expansion. Let's now look at the fractional approximation. And yes, you know it. You guessed it. Do you recognize these numbers? I bet you do. Because they're the Fibonacci sequence number. Now we stopped at 5. But what happens when we look 6 numbers after? What's the decimal expansion? And what is the fractional approximation with it? Let's compare this to the Euler constant. For the Euler constant, we achieved 2 decimal precision with 5 steps. Here we are at 12, and we only have 2 digits right of approximation. And here you can notice that it really is the Fibonacci sequence that appears in the ratios. At this point, we know what the Fibonacci sequence is. We know the golden ratio, why it's called golden, why it has these properties, because we know it's the most irrational number. But a question persists. Why is it divine? Why is this ratio been called the divine ratio for so long? It all has to do with flowers. To explain it, I found a simulation online which displays how a flower's buds would grow as a function of how much of a fraction of a turn the bud is from the previous one. So let's see what happens if the flower waits a complete turn before placing another bud. As you can see, it makes one spoke, which is not really natural. Now, let's see with 1/2. 1 over 2. We get 2 spokes, one opposite of the other. And we can see that we have 2 spokes. What about 1/3? If we wait 1/3 of a turn before placing another bud, this is what happens. We have 3 spokes. What about 1/4? That's right, we have 4 spokes. So then we can see, we saw that the number of spokes was the number at the place of the denominator. But what if we take 3 over 7? What would happen then? As you can see, it takes a little bit, but after we have the 7th spoke, we could predict. But then what about 4/7? Or 5? or 6? Well, as you can see, it's pretty much the same thing. It doesn't matter what the numerator is, because it will only affect the starting point. But after a while, there's gonna be spokes. The number of spoke as the denominator of the fraction. So from this, we can come to the conclusion that to be more efficient and not to have spoke like this, we should take an irrational number as the denominator. Let's see. Let's take pi as the denominator. As you can see, at first we have 3 spirals, but they're spirals. They are not really spokes, but at first they really look like spoke. And why is that? Because 3 is a really good approximation of pi. And after, as you can see, there are other spoke. And guess how much there is? There are 22. Why 22? Because 22 over 7 is the next approximation of pi. So we can see that we have these approximations that form as spokes or as diagonals in the shape of the flower. But then let's take another rational number. Let's take square root of 2. As you can see, at first it seems that there's no pattern at all, but after a while these diagonals start to form. What about e? What about 1 over e? That's right, you can see multiple diagonals form, and you can see that it's much more irrational than pi, because with pi we had really clear diagonals, they were really distinct. As with e here, we still have these diagonals, but we really don't have this much. Now let's look with phi. Let's look with the golden number. How much is there? What is it going to look like? Well, let's see. As you can see, it's almost like there are no patterns at all. But when you take really a moment to look at it, you can see these spirals happen. You can see them appear. And as you can see, they are how much?
You can see 8, 13, 21, and even 34. And if we were to continue, we would see all of the numbers in the Fibonacci sequence.
But why? Why 13 and
21?
Well, it's simple. Because they are the approximation of phi. You think this is all just a trick? That it's not true? Well, let's look with this. Let's look with the pineapple or pine cone. In a pine cone, you can see here that I have 1, 2, 3, 4, 5, 6, 7, and 8 diagonals. In the pineapple, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. So you can see from these two things that start with pine that we have the Fibonacci number as sequence. Unfortunately, I didn't have the time to gather other things that start with pine or to look at other diagonals, but I can assure you, and you can try in your own time if you want, to count the diagonals there is on plants and on things that start with pine. And it's almost always going to be the Fibonacci sequence. Thank you for listening.